Note 17.1 is starting the last chapter of the year. We're going to talk some more about chords and circles and see some angles that they make. So first we're going to talk about a new term, the inscribed angle. This is an angle whose vertex is on the circle and whose sides contain chords of the circle. So let's draw a little sketch here. So I've got my circle here, and I'm going to put 3 points on my circle, kind of like this. And I'm going to connect them together. That is an inscribed angle, okay? You've got this chord right here. You've got another chord right here. So the sides are chords. The vertex is on the circle. That's the inscribed angle, so right here. And we can use that to solve a few things. If we look at example 1, the first thing it wants us to do is name all of the inscribed angles and the corresponding intercepted arcs. So if I look back at my example, if this is my inscribed angle, then this is its included arc, okay, the intercepted arc. So let's look at this picture. I'm just going to pick one. I'm going to start with angle, and I'm just going to start maybe ODG. ODG. And I want the intercepted arc that goes with it. So if that's my angle right here, it intercepts that arc. Kind of looks like an ice cream cone. So it intersects arc OG. Now I'm going to come back over here and we're going to find another one. So I'm going to erase some of this for you. Let's see, we did ODG, so maybe we start next and we go DOG. So I'm going to use angle DOG. And now we need to find its intercepted arc. Well, there's DOG, so the arc that it cuts would be arc DG. We got to find one more. Let's see, I'll erase some of this for you. And you may already have it. It's taken me so long to erase. It looks like the one I'm missing might be D to G to O. DGO. Yeah, that's the one. So angle DGO. And then I'm going to come over here and I'm going to bet that it has something to do with a D and O. If DGO is our angle, then DO is our arc. So pretty easy there, you just got to recognize them. So we've got a theorem that goes with this, and it's really useful. It says, if an angle is inscribed in a circle, then the measure of the angle is half the measure of the intercepted arc. So if you have the inscribed angle, you double it to get the arc. If you have the arc, you take half of it to get the inscribed, which is what this one's going to do right here. It says, given that arc BC is 100 degrees, so this arc right here is 100 degrees. Find the value of X in circle O. Now, it's kind of hard to tell, but it looks like AC, excuse me, is a diameter. So if that's 100, then arc AB must be 80. Now, I have this little formula they wrote up here. I don't know what the inscribed angle is. It's X, but I know it's 1/2 of the intercepted arc's degree. So it looks like X is going to be 40 degrees. So if the arc up here were 100, the inscribed angle would be 50. If the inscribed angle were 10, the arc would be 20. So you got to keep it straight. Let's look at the next one. This theorem just says if two inscribed angles of a circle or congruent circles intercept congruent arcs or the same arc, then the angles are congruent. So if the inscribed angle, if the angles are congruent, then their arcs are congruent as well. Let's look at the next page. Example 3 can be kind of tough. It's really hard to look at a picture like this, but it tells us that arc ST is 68 degrees. So this arc right here is 68 degrees. Then it wants us to find the measure of angle 1 and 2. And you could stare at this for a while. It doesn't give us anything else. I can't find arc RS or PT or PR. So I'm kind of left just with nothing almost. But if you look at it this way, there's a chord that goes from R to T, and one that goes from R to S, and that 68 degrees or ST is the intercepted angle. That means angle 1 is an inscribed angle, okay? It has 2 chords for the sides, its vertex is on the circle. It doesn't look quite like the ones we already saw. But I know that the inscribed angle is half of its intercepted arc, so I take 1/2 of 68, and I get 34. So angle 1 is 34 degrees. Now, also, if I look over here, SP is a chord, and so is PT, and their intercepted arc is the exact same thing. So I know that's also got to be 34 degrees. So kind of be careful, and using like markers and pencils and marking these makes it a little bit easier. The next theorem, if an inscribed angle of a circle intercepts a semicircle, then the angle is a right angle. So look at this picture right here. This is a semicircle. We're going to say FG is a diameter. Well, I have an inscribed angle right here, right? I have FE is one side, EG is another, E is the vertex. So that's an inscribed angle. But it says in this theorem, if it intercepts in a semicircle, then it's a right angle. So if this happens, guys, no matter how it looks, that's always going to be 90 degrees. If I had one that looked like this, well, maybe I should draw a better circle there. If I had one that looked like this, that would have to be 90 degrees, okay? So that means that X is 90 degrees. Let's look at this one. It's probably the most technical. It gives us a bunch of expressions for angles, and then it wants us to find a bunch. So let's fill this out. Let's see. Angle 1 is 6x plus 11. Angle 2 is 9x plus 19. Let's see. Angle 3, 4y minus 25. Angle 4 is 3y minus 9. And then it looks like it tells us that arc PQ, this arc right here, is congruent to arc RS. It says that find the measure of angles 1, 2, 3, and 4. So we're going to have to find an X, and we're going to have to find a Y. Let's look at this triangle here first that has angles 1 and 2 in it. Since that is a diameter going PS, and this is an inscribed angle PTS, this is 90 degrees. So I know in this triangle that if this is taking up 90, that these two together are taking up 90. So 6x plus 9x would give me 15x. So that's those right there. 19 plus 11 is going to give me 30. And that's going to have to equal 90 degrees. You could add in this 90 and set equal to 180, but that's what you're going to end up with anyway. I subtract 30 from both sides. I get 15x equals 60. I divide both sides by 15, and I get x equals 4. And now it's just a matter of plugging things in. So 6 times 4 is 24 plus 11 would give me 35 degrees. And then 9 times 4 is 36 plus 19 is going to give me 55 degrees. Now we have to solve for these y's. And here's kind of the thing. If you look at these intercepted arcs again, like to make angle 3 an inscribed angle, it would have to look like that, the intercepted arc of PQ. But same thing happens here. To make 4 an inscribed angle, I get an intercepted arc of RS. And since the arcs are congruent, the inscribed angles are also congruent, which means the expressions are equal. So 3y minus 9 equals 4y minus 25, and then we can just solve. I'm going to do it at the same time. I'm going to subtract the 3y to the right and add 25 to the other side. I end up with 16 equals y. Now I can just plug those in. 3 times 16 minus 9 is going to give me 39. And since they're equal, we should also get 39 here, but you should check, because if that messes up, you should know. 4 times 16 minus 25 is also 39, so we got it. All right, let's go to the next page. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary, so they add up to equal 180 degrees. So if you have a quadrilateral like this one, all of it's inside, then opposite angles have to be supplementary. It tells us in this quadrilateral QRST is inscribed in circle C. If angle T is 95 degrees and angle S is 100 degrees, find angle Q and angle R. Well, guys, opposite angles are supplementary. So 180 minus 100 will give us Q is 80 degrees. Same thing for the other one. 180 minus 95 gives us 85. So 85 degrees. So that was pretty easy. This one says find the value of the inscribed angle. So you kind of have to take a couple of steps here. There's not a lot of work involved. What I do know is I have a central angle right here. And this is the arc that it cuts. And I know that these are congruent. So I now know that this arc is 90 degrees. But inscribed angle XZY also cuts off that angle. So this inscribed angle is half of the arc it cuts, so it's going to be 45 degrees. Let's put an arrow there. And this next one's not too tough. Find the value of x. Well, here's the arc, there's the inscribed angle. I know that this is half of that, so this is 60 degrees. Now I set the expression, 3x minus 3 equals 60, and I can solve for x. So I'm going to add 3 to both sides, 3x equals 63. I'm going to divide both sides by 3, I get my x value of 21. All right, last one. This one looks tough, but there's a couple of things you can do to make it easier. It says we've got a hexagon, A, B, C, D, E, F. It's inscribed or inside of circle O. All sides of the hexagon are congruent. Find the following. So what they told us there is if this is equal, that all these are congruent. And if all those are congruent, that means all the arcs are congruent. I know there's 360 degrees around a circle. I know there's 6 sides there, so if I do some division, I know each arc is 60 degrees. You don't have to fill the whole thing out, but... So now I can answer the questions. First, arc CD. This arc right here, that's a pretty easy one. We actually have it listed out there, 60 degrees. But the next one's talking about angle CFE. So C to F to E. And if you notice, that is an inscribed angle. I know that the arc it intercepts is 120 degrees. And I know this should be half of that because it's inscribed. So it's also 60 degrees. And then the last one, it says angle BCD. BCD. So that's a pretty wide angle. It is an inscribed angle, and it breaks off this whole arc right here. Well, if I add all those up, I get 240 degrees from those 60s, but since it's inscribed, it's half of that. I get 120 degrees. All right, guys, if you have any questions, just let me know in class tomorrow, and good luck.